Greetings to all. In today's lecture, we are going to discuss about CMOS logic circuits. In general, CMOS circuits consist of bottom we have this down network. On top of this, we have this pull-up network. Pull-up network always connected to VDD, and pull-down network always connected to ground. And in midpoint of this pull-up and pull-down, we are going to take power output. Here, the pull-down network it consists of only NMOS circuit, only NMOS, and your pull-up network consists of only PMOS transistor. Let us start with two input logic gate. So first we'll draw a CMOS circuit for two input OR gate. So that is Y equal to A plus B bar. So in general, we have this series parallel connections. If it is this basic rule, we always remember. It is if it is right here operation, then your NMOS, then your PMOS. So if it is dot operation, your NMOS should be series connection and your PMOS should be parallel connection. If it is plus operation, then your NMOS is in parallel connection and PMOS is in series connection. So if you are remembering this basic table, then we can draw easily for any given plane equation. So now we are going to draw this two input NOR gate. So NOR gate is you have this Y equal to A plus B whole bar. So it is plus operation. So if it is plus operation, your NMOS should be in parallel. NMOS should be in parallel, and your PMOS should be in series. So NMOS is connected here in parallel, and your PMOS should be connected in series. So now Y equal to A plus B whole bar. So here you can easily see this we are draw the NOR gate, two input NOR gate. So here, since all the input is contained parallel in NMOS, since it is a plus operation, and all the inputs here, the pull-up network it is contained series. So why this pull-up network and why this pull-down network? So based upon this input, so we know this NMOS, if A equal to 1, then it is going to on. If A equal to 0, it is going to be off. For example, I have this table. So in this, I call it as this my M1, M2, M3, and M4. So I'll put this table A, B, M1, M2, M3, M4, and Y. So since you have this two input, there are four possible combination: 0, 0, 0, 1, 1, 0, 1, 1. So PMOS is on when gate input is 0. NMOS is on when gate input is 1. So off condition it is quite opposite. So now A is 0 and B is 0. So where A is 0, B is 0. So NMOS is going to on when gate input is 1. So now both the gate it is receiving 0, 0. So M1 is off, M2 is off. Now both PMOS is going to on since it is 0, 0 input. So your output is now directly connected to output Y. So that means these two are on. The output is pulled up to VD. Output is pulled up to VD. Second case, A is 0, B is 1. So A is 0 means M1 is off, M2 is on, and here A is 0. So M3 is on, M4 is off. So now your output it is connected to ground through this M2, through this M2. So now output is ground. So if it is 1 0, it is quite opposite to this previous case. So this is going to be on, this is going to be off, and this is going to be off, and this is going to be on. So now output is connected to ground to the transistor M1. So output here is ground. For 1 case, both A and B is on, both A and B is on, and that means NMOS turns to both M1, M2 is on, and M3, M4 is going to be off. So output is connected to ground. So here this resembles this resembles the truth table of two input NOR gate. That is VD represent here 1, ground represent 0 0. So 1 0 0 0. Next, we are going to discuss about the second problem. That is the second one, y equal to here a dot b full bar. So it is dot operation. So your pull down network is in series. Pull down network in series. Your pull up network it should be in. So to start from here, VD here. For A, for B, and here it's y equal to A dot B full bar. So now to analyze this, we will name it this transistor M1, M2, M3, M4. So put this A, B, then M1, M2, M3, M4, then Y. So since you have to input four possible combination 0 0 0 1 1 0 and 1 1, A is 0, B is 0, M1 is off, M2 also off, M3 is on, and M4 is on. Your output Y is connected to VD, so Y equal to VD. If A is 0, M1 is off, B is 1, M2 is on, and M3 it is going to be on, M4 is going to be off. So now your output is connected to VDD to the transistor M3. So output here it is VD. If A is 1, B is 0, it is quite opposite to this previous condition. So it is going to be on, it is going to be off, and it is going to be off, it is going to be on. Now your output is going to VD to M4. So you're getting output VD. So in the case of 1 1, it is quite opposite to a 0 0 condition. So M1 is on, M2 is on, your M3 is off, your M4 is also off. Your output is kind of now ground through your M1 and M2. So here the output is 1 1 1 0. So the next we are going to discuss about three input CMOS circuit. So third one y equal to a plus b into c. So in this problem we have this both OR operation and dot operation. So we know this, if it is OR then we ought to put NMOS transistor in parallel. So here the OR operation belonging to A and B. So it is A, it is B, and here it is we have dot operation. So dot operation we have to get in series with this parallel connection. So here it should be C, and here it is connected in ground. It should be connected to output Y equal to A plus B into C whole bar. So here whatever we are putting parallel in PMOS, it should be in series, and whatever you're putting here in series, that should be in parallel. So we have here, so here's my VDD, and here this leg should be my A and B, and here is C. So whatever you are having here parallel, here it is series, and the series connection whatever you have here, it should be in parallel. So here Y equal to A plus B plus C into C whole bar. Okay. So next problem we are going to see the fourth one. So fourth one, Y equal to A dot B plus C whole bar. So here we have this A and B series, and C is parallel to this A and B. Is connected to output Y. If this series, so here it should be in parallel. So here is my A, B, and series with this is C. So here's where A dot B plus C whole bar. Okay. So next we are going to discuss about stick diagram. So in VLSI there are two kind of layout diagram. One is what we call as stick diagram. So stick diagram will help us to draw the layout diagram. So what is the difference between stick diagram and layout diagram? Stick diagram we are going to draw without any dimension, but layout diagram we have to draw using with dimension. So this is a major difference. While we are draw the stick diagram we are drawn without any dimension, but layout diagram we draw with dimension. So we know this. So whenever we draw this stick diagram, so the first step we have to draw with this CMOS logic gate. So CMOS logic gate, we already have this for two input OR gate. Sorry, so A, and there's a B, is a A, is a B, and there's a Y, and here is VD, and is a ground. Okay, so we know this whenever you draw this stick diagram. it is better use this color, suitable color. So for VD and ground, VD and ground, so we are using black color. Okay, so if it is um, N plus region, that is for whenever we draw this CMOS transistor, we need P plus for NMOS transistor we need N plus. So here P plus we are going to draw using green color. P plus P plus we are draw using yellow color, and N plus we are to draw using green color. Our polysilicon to use red color. So when our polysilicon cross our P plus N plus region, then one transistor is coming. So here these are VD and these are ground. Okay, so for connection of this output, you have to use blue color. So how to draw this tree diagram? So here and represent this my A and this my B. That is whenever the polysilicon cross this P plus region and N plus region, based on transistor is forming. So here this polysilicon it is crossing P plus region. This is one PMOS transistor. This is another PMOS transistor. Here one NMOS that is A NMOS transistor. This is P NMOS transistor. So here we see this from VD. It is going this one end of your A. That means here it is source. Yes, it is drain. Drain. It is drain. Source. It is drain and source. Source. Okay, so if we know this, we can interchange drain and source. But however, this so we have to follow these rules. From VED, A transistor it is going like this. From VED, it is going like this. It is one end of this A transistor. So we are connecting here. So now A this end is connected to this diagram. Then A at the end and B one end it is connected in series. So this portion of the diagram. Then B another end connected to output Y. Output Y. So with respect to this NMOS transistor, so here both A and B is shorted and given to ground. So common point is both A and B is here. So this should be connected to ground. So other end of both A as well as other end of B, it is going to output Y. Output Y. So here I will take like this and you connect like this and it should be connected to output Y. This is the diagram for two input NOR gate. Similarly, for this stick diagram for NAND gate. So NAND gate, your CMOS transistor, it is connected in parallel. A, B. It is output Y. It is equal to A dot B whole bar. It is VDD. It is ground. Okay. So these were VDD and this ground. These were P plus. So P plus and so N plus and polysilicon. Once again, we have this. These are A and these are B. So if you are saying this, your B1 end is connected to ground. B1 end is connected to ground. So here connected to ground. So here it is like this. It is going like this. B1 end is connected to ground. Then other end of B and A it is shorted. Then it is going to output. So here it should be taken to output. Similarly here this midpoint of your A and B is connected to VD. Midpoint of A and B is connected to VD. So A other end and B other end is shorted and given to output Y. If it is 2 input or 3 input CMOS circuit, then drawing this stick diagram it is very easy. So there is no issue on putting this variable in the polysilicon. However, if there is more than 3 input, then we have to follow the Euler path. So Euler path. So what it means by Euler path? So Euler path is a path through all the nodes in the graph such that each edge is visited once and only once. So we will solve. That means we are going to draw this stick diagram using Euler path. Okay. So for this, we will take this the problem. So here y equal to x plus y z equal 1. So here we have one OR operation, one dot operation. So if you draw this CMOS circuit, these were y and z, and here these were x and these were x, these were y and Z is connected to ground. So now to follow this idle path, first you have to draw this graph for PMOS and here's for NMOS. So here is our VDD and here we are taking, sorry, here we are taking our output. Okay, so with respect to this VDD, here's our another node. So here we are having output. Okay, so it is like this, edge like this, and it's going like this. And for this output and with respect to ground, so here we have node, it is like this. So from here to here it is y. From here to here it is z. There is nothing but x, and here is our x, y, and z. As per the definition of Euler path, we have to visit all the nodes in the graph such that each edge is visited only once. So if you are starting from here, that means from this point, I will go like this, I will go like this, and I will go like this. That means I visited only once. So it is possible z, y, x. Similarly here I can go like this. So R is there. So z, y, x. The other path I can go like this. So y, z, x. Here also I can go like this. So y, z, x. Otherwise I can go starting from x. I can go like this. Okay, so it means x, y, z. So here also I can go this x, y, z, x, y, z. So like that we are getting different path. So that means here this is also same, this is also same. So what we are going to get? We are going to get the transistor order. Either we can follow y, sorry, z, y, x, or y, z, x, or x, y, z. So this is very small problem that we have only three input. So we are getting both PMOS and NMOS in same order. But there are certain cases we are not able to get this transistor address both NMOS and PMOS is not same. Okay, so here Euler path will help us to find the order of the transistor. So we can put this polysilicon either YZ, YX or YZX, XYZ. So here both are having same order of the transistor.